Hey guys, welcome to day 13, lucky 13. We're going to start off by talking about limits analytically. Now, as a preface, the idea of doing limits analytically is to avoid the two previous methods. As you can imagine, if you were doing this by hand, the numerical method where you use the table and put in values around the number would be very frustrating if you didn't have a calculator. And so, for a long time, mathematicians searched for other ways to approach this problem that didn't want to do that. Because if you're forced to do it by hand, you don't want to have to, plug in numbers of, a millionth or even a thousandth in order to get close to your answer. You'd rather just solve it like you would algebraically. And the analytical approach is designed to be the algebraic approach, where you solve it algebraically as opposed to plugging in numbers. And the same thing with graphing. Before the advent of graphing calculators or graphing computers, solving these problems with a graph was very, very difficult because you had to know how to graph them perfectly, because if you make even a single mistake, you might be led to a different limit. And while some functions are very easy to graph, like we saw last time with that sine function, or a sine of 1 over x, that's very difficult to graph and to be able to predict what that graph would look like without having to plug in a lot of values. And so it's very, very, very important to understand that the analytical approach is the primary way we'll do a lot of our mathematics from this point on. The other methods are good because we have these tools available to us. But because mathematics existed long before calculators and computers, most of the approach of calculus is doing it without them. And so that's why we have the analytical approach. So we're going to talk about a lot of theorems today. And we will not get fully into the analytical part, the part that's the fun part, until next time, when we actually use a lot of algebra to solve these things. What we're going to do today is to verify a lot of things that you probably assume about limits to be true, or at least would be natural to assume once you've seen a few of them. And from there, we're going to look at how to solve them algebraically next time. All right, let's get started. Okay. So we got a whole slew of theorems today. We're going to go through probably 6 theorems, and each of which has a different part. So I'm going to start labeling. Let's start with theorem number 1. Now, this is the first theorem in the first chapter. So my typical notation is theorem 1.1 because it is the chapter 1's first theorem. And most calc books and other textbooks do it that way. So these are referred to as your basic limits. These are limits where you'll never have to do the numerical approach or the graphing approach ever again. And in this case, we're going to assume b and c are integers, or I guess they could be real values. So it could be fractions, it could be decimals, it could be radicals, but in this case we have to assume that n is positive. That'll come into play here in a second. Okay, first part. The limit as x approaches c of a number. So in this case, this could be 5, this could be 12. C in this case is unimportant because the limit as we approach a number is just the number. We'll look at an example of that in a second. Second part, B. The limit as x approaches c of x will of course be c. And the third part, the limit as x approaches c of x to the n power would be c to the n power. Let's showcase what this means using some examples. So let's look at the limit as x approaches, this number can be any number for this to work, but let's go ahead and go to 0, of 5. Now you might be looking at this and going, well, isn't the answer 0? No, not even close. The answer is in fact 5. Because what this statement is saying is, hey, what happens as x approaches 0 to the equation 5? Well, since there are no x's that actually approach 0 in this equation, the fact that the x is approaching 0 is inconsequential, meaning that we're really asking the question, hey, what's 5? And the answer is, of course, 5. Because there's no x for us to simplify into, there's no way to plug into this equation and therefore pop out an answer that's anything different than 5. If we were to use the table approach, right? Just do it very briefly under here. Hopefully for the last time. We're approaching 0. This would be negative 0.1, negative 0.01, and negative 0.001, 0.001, 0.01, and 0.1. Well, if we plug into this list, well, when I plug x is 0, what does this number become? Well, it's still 5. When I plug in this number, it's still 5. When I plug in this number, it's still 5. When I plug in this number, it's still 5, still 5, still 5. Because plugging in x is 0 doesn't do anything, so the answer is, of course, just 5. And so if you ever see the limit of a number, it is just the number. And the same thing can happen here if we do the limit of x. So if I do, for example, the limit as x approaches 3 of x, well, that's just going to be 3. And I can prove that with my table again, using the numerical approach. Okay, so 3 is in the center. This would be 2.9, 2.99, and 2.999. And over here you'd have 3.001, 3.01. I apologize that it's getting so cramped, and 3.1. But if it's just x, then when I plug in 2.9, I'm going to get out 2.9. When I plug in 2.9, I'm going to get out 2.99. When I plug in 2.999, I'm going to get out 2.999. And on the top side, if I plug in 3.1, I'm going to get 3.1. If I plug in 3.01, I'm going to get 3.01. And 3.001. So you can clearly see that these are merging at 3. And if I do the n power, the same basic thing happens. We end up with the limit as x approaches, let's do a negative just for fun, negative 2 of x. In this case, n can be any power, so it could be an unknown power. So I'm just going to leave it as n. Well, this is just going to be negative 2 to the n power. And again, if we use this approach, that's exactly what happens. In other words, numbers stay numbers, x's get plugged in, x to powers get plugged in. So basically, theorem part 1 can be summarized as you plug in if it matches these 3 scenarios. If it's a number, you don't do anything, it's just a number. If it's x, you just plug in. If it's x to the n, you just plug in. So that's our first theorem. Theorem number 2 is a bunch of properties. Now for this to work, this will be the fun part of our homework for tonight, because the properties have to work for you to keep looking at this. We're going to assume a couple basic things. We're going to assume we have 2 limits that are known. So you have the limit as x approaches c of f of x equals the number L. So again, L can be any number. And we have the limit as x approaches c of g of x equal to a different number. Okay? So we have 2 separate limits, the limit of f, the limit of g. Notice they're both approaching the same value, but they output different values. Now they could output the same values, like L could equal k, that doesn't matter too much. But these are going to be our basic assumptions here. Okay, first basic property. We call this scalar multiplication. What it says is, if I take the limit as x approaches c of b times f of x, in this case b, again, is going to be a real value, so it could be 7, it could be 2, it could be negative 4/3, it could be a radical. 2 things happen. 1, we could take the b and essentially bring it outside. Meaning that b, as a number being multiplied to a function, you can do the limit of the function instead. Now, because we know this limit from the given, this means we end up with b times L. In other words, if we have something like, let's say the equation, the limit as x approaches 3 of 6x, we could use the scalar multiplication to bring the 6 to the outside, and then use theorem 1.1, the second part of it, to plug in. meaning the limit as x approaches 3 of 6x is 18. In other words, it can be summarized as plug it in. So this allows us to take a function that is multiplying to one of our previous basic limits and rewrite it as, a multiple of that basic limit. B. And we'll do lots of examples of these because these are like the big deal for today. B. If I have, and this is the sum difference, if I have the limit as x approaches c of f of x plus g of x, so in other words, or minus in this case, it could be either one. If I have two things inside a limit being added or subtracted, so I have f of x, I have g of x, they're both inside my limit, and they're being either added or subtracted, what I can do is I can break that big limit into two smaller limits. So I can take this big limit with two pieces inside of it and break it into two smaller limits. So if I was to take something like, this is our example to go with this one. If I was to take something like the limit as x approaches -1 of x minus 4, this is not one of my basic limits, okay? But what I could do is use this sum difference property to say, well, I'm not going to look at it as one limit, I'm going to look at it as two limits, each of which is a basic limit. And so now I can do this bottom piece using our property up here, which says we just plug it in, so this piece would become -1 minus, and then I can use this first property to do this limit. But this should make a lot of sense, because this is a lot of algebraic properties that we've used for a long time, right? You're always capable in a mathematical problem to factor a b out of it, as long as b is a constant. You're always able to take addition and subtraction and look at them as separate identities that you can then put back together if you need to. Like, these are all basic things that we've used for years. It's just now we're applying them in a way that we have to make sure makes sense with the calculus. And it turns out the things that make sense with calculus work. Okay, we have two more here that are really similar. We have the product and the quotient. And then the last one is the power. Okay, the product. If you have the limit as x approaches c of f of x times g of x, you can view this as two separate limits. Times the limit as x approaches c of g of x. So you notice that the operations inside don't change, right? This is a plus minus in the limits. This is a plus minus between the limits. This is a product in the limits. This is a product between the limits. For this one, well, f we know is L, and this we know is K. I didn't do that for the top one. I should make sure to get that in here. This is equal to L plus K, of course. In other words, I can take these limits and do them separately, whether they're being added or subtracted, or whether they're being multiplied. And as you can imagine, if we have a quotient, that's going to be division. The limit as x approaches c of f of x over g of x. You can look at it as splitting the limit apart, one on top and one on bottom. But through basic substitution, we know the limit of the top would be L, the limit of the bottom would be K. However, this is the only one that is sneaky. K cannot equal 0. Meaning, if we want to use this particular property, the bottom function, yes, I said function, g of x is a function, can never equal 0. Because if it equals 0, you're never allowed to divide by 0. That's a calculus rule as well as an algebra rule. The power one says the limit as x approaches c of f of x to the n power. What we can basically do is we can move the limit inside. I'm going to move over here a little bit. So the limit as x approaches c of f of x, we put it to the n power. So we can basically take the limit and put it inside a power, and thereby be able to get, L to the k power, or L to the n power. It allows us to take functions that before were unable to simply do using these basic approaches, right? Because from theorem 1.1, there's only 3 things you can do a limit with. You can do a limit with a number, x, or x to a power. But now with these rules, look how many doors we've opened. You can now do it if something's being multiplied to one of the above ones. So like a number times a number, we can do it with this rule, or we could do it another way. A number times a variable, we could do it with this rule. A variable with a power times a number, we could do it with this rule, right? We can take x and x squared and do their limits, because if they're being added together, we could do them separately. Or if they're being multiplied or divided. Like this opens whole new fields to us. Just using these 3 basic ones combined with all these possible ways we could do them, we can start to do more and more complex limits without needing to use things like the numerical approach or things like the graphing approach. Now let's take a look at an example. Let's see, where's my first one? Let's take a look at this limit. If I want to do the limit as x approaches 2 of 4x squared plus 3x minus 1. Okay, first thing to point out here that is really frustrating is without the previous 2 theorems, without any of these things up above here, I cannot evaluate this limit except by doing the numerical approach or the graphing approach. Like, I have to do one of those 2. However, using these theorems and their properties, I can take this equation and rewrite it in such a way that I can get the answer without needing to do these steps. Now, for these first couple, I'm going to show all of my work. After that, you should start taking some shortcuts. We can know where this is going to go very quickly. Okay? So, for this one, the first thing I'm going to do, my first step is going to be, I'm going to use the sum difference rule. So what does that mean? It's going to take this big limit, which contains 3 separate terms, and it's going to break it into 3 small limits. The limit as x approaches 2 of 4x squared minus the limit as x approaches 2 of 3x plus, it should be plus, and that's what should be minus, the limit as x approaches 2 of 1. So I use my sum difference rule, which says that if they're being added or subtracted as a big limit, I can break them into smaller limits. Now, second step, I can use the scalar multiple on the first 2, and then I can actually go ahead and do the last one. Let's take a look. So these first 2, this will become 4 times the limit as x approaches 2 of x squared plus 3 times the limit as x approaches 2 of x minus the limit of 1. According to our basic theorem list, the limit of a number is just the number, so the limit of 1 is just 1. Now, according to the other parts of our theorem, right, the limit of x is just c, so in this case, this would become a plus, this becomes a minus 1, so 3 times this limit would actually be 3 times 2. Because according to our theorem 1 and our second part of theorem 1, the limit as x approaches 2 of x would be just the number 2. Over here we can do the same thing, 4 using this third part, which would become 2 squared. This allows us to actually algebraically solve this limit. So this becomes 4, 16, plus 3 times 2, that'd be 20, minus 1, this would be 19. Wait, Douglas math? No, Douglas can't math. 16 plus 6, not 4, duh. That'd be 22 minus 1, this would be 21. Dumb Douglas. Alright. So what this does is it allows me to algebraically solve a limit, because I can actually do this. And this actually leads us to our next theorem, and a property of polynomials, and why polynomials are so heavily discussed in algebra classes. This is theorem 1.3. The theorem states, if you have a polynomial function and you have a real number c, this is referred to as the polynomial, or the limit of a polynomial. What it states is, this limit, as x approaches c, of any polynomial function. Remember from algebra, the polynomial function is any collection of terms where the x is being to an integer power, so, or I guess there would be a whole number power. So it'd be x squared, x cubed, x to the fourth, any of those would work. The limit of p of x would just be p where you plug in c. In other words, and this is where we start to have to understand math a little bit better, what this means. You have to think, what is a limit actually doing? A limit is saying, hey, where do we think the answer is? Or what is the expected answer? And so what it says is, for all polynomials, the expected answer is the same as the actual answer. That's a big detail. Okay, that's what makes polynomials so useful, is that if we expect to get C, we should get C. If we expect to plug in 5, we should get the answer when we plug in 5. It's not going to randomly jump around to a new spot, right? It's not going to have, the phrase that we're going to use a lot in this class is called continuous. What it means is, if you have a line that's not continuous, there's a place where the line suddenly breaks and does something else. If you're looking at this graph, like, your expected value from one side is different than your expected value from another when we get to this point. Well, this never happens in a polynomial. This cannot possibly happen in a polynomial. Your expected value is the same as your actual value. Now, what does this mean? There's also a secondary part of this theorem. This is referred to as the rational equation theorem. So we have to have a rational, where in this case the rational is equal to p of x over q of x. Remember, a rational function is any function where the top part of a fraction is a polynomial and the bottom part of a fraction is a polynomial. However, the only big thing here is q of c cannot equal 0, because you can never divide by 0. However, what we have here is the limit as x approaches c of r of x is equal to r of c, or, of course, p of c over q of c. In other words, as long as the bottom doesn't equal 0, again, your expected answer is the actual answer. So we can actually plug in and go. So take a look at this function. Let's see the limit. Example. Let's start with the simple one. What if we had the limit as x approaches 2 of x squared minus x plus 1? According to the first part of this theorem, this is going to be equivalent to just plugging 2 into this equation. 2 squared minus 2 plus 1. Which makes sense, because again, the expected value is the same as the actual value, meaning not only do we not need to do the numerical approach or the graphic approach, we can literally just plug it in and go. Meaning that this limit can be found just by plugging it in. 2 squared is 4, minus 2 is 2, plus 1 is 3. What it also means is, if it's rational, as long as the bottom doesn't equal 0, this also works. So if I had, for example, x squared plus x plus 2 over x plus 1, you'll notice that if I plug in 1, the bottom is not equal to 0, which means that I can literally just take the 1 and plug it in. And solve it algebraically. 1 squared is 1, plus 1 is 2, plus 2 is 4. 1 plus 1 is 2. 4 over 2 is, of course, 2. And so as long as it meets one of these criteria, right, where either it's a basic function, it's some augment of a basic function, like being multiplied by a constant, being added or subtracted, being multiplied or being divided, with the division never equaling 0, or if it's a polynomial or a rational. If it meets one of these criteria, it's essentially you can just plug in and you get the limit. Now you can verify all of this. You always have the option, you can verify numerically. So I could go back and, plug in numbers around 2, plug in numbers around 1, and get the same answer. Or I could do it graphically. And again, I could look at the graph and see what's happening around x value of 2, what's happening around the x value of 1. And I should get a y value of 3 or a y value of 2 out of it. It makes sense because algebraically, polynomials and rationals are the simplest functions. Now, next theorem. This will probably be the last one of the day. Theorem 1.4. Okay, in this case, n needs to be a positive integer. This is true if n is odd and c greater than 0. Okay, so we have the limit as x approaches c of n square root of x is equal to the nth root of c. In other words, if I have a radical, I can just plug it in same as I can before, provided that it's odd and that c is bigger than 0. Now, this works for all values of c if n is odd. It works for c bigger than 0 if n is even. So if n is an odd number, like say the cube root, you can do this for anything. Any value of c could be -7, could be positive 24, doesn't matter. But you just plug it in. However, if the n is even, this is a problem, because square roots, we have the possibility of getting imaginary answers. Fourth roots is the possibility of imaginary answers. And so you have to be careful to make sure we should have no imaginary answers. No imaginary answers in calc for now. If you go farther in mathematics, things like Calc 2 and Calc 3, like the classes you take after Calc 1, you can start talking about what imaginary numbers do in calculus. But calculus is meant to be a very real system. It's meant to showcase a very real set of numbers and data and usages. So imaginaries don't come into play until much farther along. Kind of like you don't talk about imaginary numbers in math until, you're in high school. Okay. The last one I'll give up here. This is theorem 1.5. States that if you have two functions, f of x equal to okay, so we have that, and we have a secondary one, limit as x approaches c of g of x. So these two, these seem kind of weird. These are your pre-existing conditions. These are your assumes. What the states is, take the limit as x approaches c of f of g of x. You can take that limit and put it inside, so we'd have the limit of f so the limit can essentially move inside a function, and then you just take the limit of that function. The limit of this function is L, so this would be f of L. Which is, unique because, previous mathematics, for example, if I was to look at this function as, example, the square root of x squared minus 4x, limit as x approaches 6. I, can use properties to solve this limit because of a couple different pieces. First one, I can use theorem 1.5. Theorem 1.5 states that I can take this limit and rewrite it as the square root of the limit as x approaches 6 of x squared minus 4x. So I can take that limit that was on the outside and rewrite it as being on the inside. And this one on the inside is a polynomial. So I can use the polynomial function in order to just basically plug in 6. This becomes the square root of 6 squared minus 4 times 6. 6 squared is 36 minus 24. So this becomes the square root of 12, or 2 square root of 3. It offers these really cool, unique ways to solve problems that, again, don't fit our list. This is the only list we have of things that we can find the limit of via the analytical approach. But because we can do it in all these other different ways, using theorem 1.2, 1.3, 1.4, and now 1.5, we can rewrite functions in a lot of different ways to be able to solve them, which is pretty unique. Now, for tonight's homework assignment, there are two different types. The first half, or should I say the first 3 quarters, is just basically plug and chug. You can use the theorems. You don't have to show all your steps like I did, but you should make sure to verify that your solutions are right. And the second half deals with it more of as an abstract concept. Those will probably be the harder ones, and I think they'll be the more rewarding ones if you get them done. So, this will be it for today. I hope you guys have a happy Tuesday. I look forward to seeing you guys tomorrow, and have a good rest of the day.